This movie deals with rectilinear motion, that is, motion in one dimension. It is intended for viewing before students do a laboratory experiment on free fall to determine the acceleration due to gravity. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to recognize and interpret plots describing constant speed and constant acceleration, determine the acceleration due to gravity from measurements using a photogate timer of positions of a freely falling body versus time. To describe the motion of an object, we need to know its location and a function of time. Since we live in a three-dimensional world, we need three numbers or coordinates in order to specify the location of an object. For simplicity in this lesson, we will focus our attention on one-dimensional motion. To locate an object in one dimension, we need to select some location as the origin. Then the location, which we will refer to as x, or y, or z, is simply the distance of an object from the origin. In other words, the object's location is simply the distance from the origin. We also assign an algebraic sign to our location to indicate which side of the origin the object is located. There are cases where the motion of an object can be concisely described by a mathematical equation. If a plot of the location versus time is a straight line, then the equation that relates location to time is given by x equals some constant, shown here as x naught, plus another constant, shown here as v times t. In this equation, x is the location of the object at time t. You will recognize this equation as the equation of a straight line. The variables x and t represent the vertical and horizontal coordinates, while the constants v and x naught are the slope and vertical intercept, respectively. If this is the case, we say that the object is moving at a constant speed equal to v. Let's see why. You will recall that speed is defined as distance traveled per unit time. Mathematically, this is written by dividing delta x, which is the change in location of the object, by delta t, which is the elapsed time. If the plot of x versus time is a straight line, then we know that the ratio of delta x to delta t is a constant, and it is simply the slope of a straight line. You will note that the slope of a straight line can be positive or negative. Since slope is to the speed, exactly what does a negative speed mean? A negative speed simply means that the object is moving toward locations that we have assigned to lower numbers. Conversely, a positive speed means that the object is the other direction, that is, toward locations that we have assigned to higher numbers. The slope of a straight line can also equal 0. What does this mean? If the slope is equal to 0, that means the plot of x versus time is a horizontal line. This means that x does not change even as time advances. Therefore, we can say that the object is not moving, or that it is at rest. In other words, its speed is 0. Consider the plot shown here, which keeps track of the location of an object, x in meters, versus time in minutes. Taking the positive x direction as motion to the right, which segments of the plot correspond to a situation where the object is moving at a constant speed to the right? For the time interval corresponding to each straight line segment, we can say that the object is moving at constant speed, and that the speed is equal to the slope of the line. A positive slope means that the object is moving toward locations with higher x values as time passes. This is the case from about 3 to 6 minutes. The object moved from the 2-meter location to the 5-meter location. The object moved 3 meters in 3 minutes. You could see from the graph that for every minute that time advances, that location advances by 1 meter. Thus, the slope is constant and is equal to 1 meter per minute. We say that the object was moving at a constant speed of 1 meter per minute during the 3 to 6 minute time interval. How about the segment from 6 minutes to 9 minutes? This is also a straight line segment with a slope of 3 meters per minute. Note that the slope is steeper from 6 to 9 minutes as compared to the 3 to 6 minute time interval. The steeper the slope, the faster the object is moving. Next question. Which segment in the plot represents constant speed to the left? Since we have defined the positive x direction as going right, moving left means moving toward lower x values. This is the case from 10 to 15 minutes. Since the segment is a straight line, we can say that the object is moving to the left at a constant speed. The object moved from the 14 meter location to the 4 meter location during this 5-minute interval. Since it moved 10 meters to the left, we say that delta x is negative 10 meters. Divide that by 5 minutes, we get a speed of negative 2 meters per minute. You should easily see from the graph that during this interval, for every minute that time advances, the object moves 2 meters to the left. For example, from 10 to 11 minutes, the object moved from the 14 meter location to the 12 meter location. Next question. Do you see any segments that represent a situation where the object is not moving? The answer is yes. These are situations where the location does not change even as time advances. The horizontal or flat line segment represents zero speed. The slope of a horizontal line is 0. Finally, during which time interval is the object moving the fastest? Mentioned earlier, the steeper the slope, the faster the speed. During the 6 to 10 minute time interval, the slope is steepest. Studying the motion of an object gives us insight about the forces acting on it. Newton's second law of motion says that if an object is at rest or moving at constant speed, then the net force on the object is 0. If an object's speed is changing, we say it has non-zero acceleration. Newton's second law of motion says that the acceleration depends on the forces acting on the object as well as the mass of the object. If the force acting on the object does not change even as it moves, then its motion is said to be uniformly accelerated. We will observe constant acceleration. How can we tell if an object has a constant acceleration? We can tell if we plot its location versus time and find that we can fit the data to a quadratic function of time. We would be able to fit the data to an equation of the form x equals x naught plus v naught times t plus 1/2 times a times t squared. In this equation, x is the location of the object, x naught is its initial location, that is, its location at the time we select as time 0, v naught is the initial speed of the object, and a is the acceleration of the object. In this equation, x naught, v naught, and a are constants. Acceleration is defined as the change in speed per unit time. That is delta v divided by delta t. Since v is positive if the object is moving in the positive direction and negative if moving in the negative direction, acceleration also has an algebraic sign associated with it. Acceleration is positive if the object is speeding up while moving in the positive direction, or slowing down while moving in the negative direction. Conversely, acceleration is negative if the object is slowing down while moving in the positive direction, or speeding up while moving in the negative direction. Alternatively, we can plot the speed of the object versus time. If the object is uniformly accelerated, we will get a straight line with slope equal to the acceleration, a. An object in free fall is an example of a uniformly accelerated object. Its acceleration has been found to be pretty much a constant value of 9.8 meters per second squared anywhere near the Earth's surface. The acceleration due to gravity is typically represented by the symbol g. What equations would we use to describe a freely falling object, taking the direction toward the ground as the positive x direction? If we take the moment the object is released as our time 0, or our initial time, then v0 is 0. Since v equals v0 plus a times t, v will simply be equal to a times t, or g times t. In other words, the speed is proportional to the elapsed time. The more time has elapsed, the faster the speed. In fact, for every second, the speed increases by 9.8 meters per second. We say that the acceleration due to gravity is 9.8 meters per second per second. Similarly, to describe the distance traveled versus time, we get x minus x naught equals 1/2 times g times t squared. The equations shown here for a uniformly accelerated object are actually applicable to any object moving at constant speed or any object at rest. For example, if a is equal to 0, then v equals v0, which is a constant. In other words, zero acceleration implies constant speed. For an object at rest, we simply plug in 0 for a and v0 in the equation shown here. Consider the following plots of the speed of an object versus time. How would you describe the motion of the object? The plot on the left shows that the speed increases at a constant rate as time passes. Since the plot is a straight line, we could say that the object is uniformly accelerated and that the acceleration is equal to the slope of the plot. It is easy to see from the graph that the speed increases by 10 meters per second every second. Therefore, the acceleration is 10 meters per second squared. The plot on the right also shows a straight line dependence of speed versus time. Therefore, the object is uniformly accelerated. We can estimate the slope easily. We can see that the speed dropped from 50 meters per second to 10 meters per second in 5 seconds. That's a drop of 40 meters per second in 5 seconds, or 8 meters per second per second. Note that the acceleration here is negative. Consider the following plots of the location of an object versus time. How would you describe the motion of the object? You will note that in both cases, the data points were fitted to a quadratic equation. Therefore, we could say that the object is uniformly accelerated. For the plot shown on the left, x equals 5 times t squared. We can identify 5, the coefficient of t squared, as 1/2 of the acceleration. 5 is half of 10. Therefore, the acceleration is equal to 10 meters per minute squared. We can see from the graph that the curve is getting steeper with time. The object is speeding up at the rate of 10 meters per minute every minute. For the plot shown on the right, we can identify negative 7.5, the coefficient of t squared, as the 1/2 of the acceleration. Therefore, the acceleration is negative 15 meters per minute squared. We can also identify 20 meters as the initial location, and 50 meters per minute as the initial speed. You will note that from 0 to about 3 minutes, the slope of the curve becomes less and less steep, and it's almost flat just after 3 minutes. That means that the object is slowing down. According to the equation, it is slowing down at the rate of 15 meters per minute every minute. That means at around 3 minutes, its speed has dropped by 45 meters per minute to 5 meters per minute. In fact, shortly after 3 minutes, around 20 seconds after, the slope is flat and the object starts moving in the opposite or negative direction. The slope is now in fact negative. The speed is negative. The object, we say, still has an acceleration of negative 15 meters per minute squared. But since it is now moving in the negative direction, it is actually speeding up. As time advances, we could say that the speed is becoming more negative. Shown here are pictures of the materials and apparatus that you will use for this experiment. The purpose of the experiment is to verify that a freely falling object is in fact uniformly accelerated. You will determine from your data the value of the acceleration due to gravity. You will use a photogate detector to time the motion of a piece of plexiglass that has alternating black and clear sections. The plexiglass is labeled here as the picket fence. You will drop the picket fence between the J-shaped bracket of the photogate detector, which is hooked up to a computer. The electrical signal from the detector depends upon whether or not the light from one side of the J-shaped bracket reaches the other side of the bracket. As the picket fence passes, the electrical signal is alternately blocked and up by the black and clear sections. You will use a stick to measure the distance from the leading edge of one black section to the leading edge of the next black section. They should all be equally spaced by 5 centimeters. Use a piece of styrofoam to prevent damage to the picket fence when it hits the bottom. We used the photogate timing program from Veneer software to collect data for this experiment. The program we have in the laboratory is an old one, but it runs in an MS-DOS box from Windows. The program is menu driven. It gives you a menu of what you can do as shown here. You select from the menu by pressing the up or down arrow keys on your keyboard until your choice is highlighted. Then press the Enter key. Alternatively, you can simply press the letter corresponding to your choice. On the main menu shown here, for example, you press M to access the motion timer, S to check if the photogate is working, and Q to quit. Before you drop the picket fence between the J bracket of the photogate detector, first make sure that the detector is working properly and is communicating with the photogate timer program. At the main menu of the photogate timing program, press S to check the status of the photogate. It should say that the detector is unblocked. Wave your hand between the J-shaped bracket as you pass the detector. The status shown on the screen should change to blocked. If your photogate is not working, ask your instructor for assistance. Otherwise, press Enter to return to the main menu screen. This experiment does not take very long to do. Once your photogate detector is set up and connected to your computer, and you have verified that it is communicating with the photogate timing program, simply select Motion Timer from the main menu. The program will then prompt you to drop the picket fence and display the results. Copy the data to your notebook. You should have 2 columns, one for row number and the other for time. Time for row 1 refers to the time elapsed from when the leading edge of the first black row passes the detector to when the leading edge of the next black row passes the detector. Similarly, the time listed for row 2 refers to the time it took for the picket fence to drop from the leading edge of the second black row to the leading edge of the third black row. Once you have collected your data, there are other things that the program allows you to do. Feel free to explore these other program options. All you really need is the raw data. All data will be analyzed in an Excel spreadsheet. Open an Excel document to analyze your data. Tabulate the row number in column A and the time it took to traverse each row in column B. Calculate the average speed of the picket fence as each row passed through the detector, knowing the picket fence fell through a distance of 5 centimeters as each row traversed the detector. Tabulate and plot displacement, y, of the fence versus time, t, taking the leading edge of the first row as y equal to 0, and the time when this leading edge passed through the detector at t equals 0. For example, by the time the leading edge of the second row passes the detector, the leading edge of the first row has already fallen 5 centimeters. It would have already fallen 10 centimeters by the time the leading edge of the third row passes the detector. Put the Y values in column D of your Excel document. In column E, enter times when the leading edge of each row passed the photogate detector. Plot the displacement, Y, of the fence versus time. These are columns D and E of the Excel document. As mentioned earlier, we use the leading edge of the first row as the reference and take the time when that happened as our initial time. Add a quadratic or second-order polynomial trend line to your plot. Click on the Options tab of the trend line window and check appropriate boxes to force the intercept to 0 and display the quadratic equation on the chart. From the equation, you should be able to determine the initial speed of the fence. This would be the coefficient of t, and the acceleration due to gravity. This would be 2 times the coefficient of t squared. Note that we do not expect the initial speed to be 0. The fence would have already fallen a certain distance and sped up by the time the first row passes the detector. Remember, we have chosen this, not the moment we release the fence, as our initial time. An alternative way of analyzing your data is to plot the speed of the fence, column C in your Excel spreadsheet, versus time, column E in your Excel spreadsheet. You should get a straight line with the slope equal to the acceleration due to gravity. Since v is the average speed as a given row passes through the photogate detector and not the instantaneous speed at time t, the instant when the leading edge of the row passes through the detector, method 2 is less accurate than method 1. Calculate more accurate values of v using v0 and g values for method 1. V equals v0 plus g times t. Set this up in column F of your Excel spreadsheet. Calculate percent discrepancy between v values for methods 1 and 2. Explain the trend. Why are the v values for method 2 larger? Why does the discrepancy decrease versus row number? A hint is to examine the trend in the time it takes to traverse the rows. How would you modify method 2 to improve its accuracy?